Good morning, all. Welcome to the session of computer architecture. So, with the series of computer architecture, we are going to see in this session the concept of cache memory. So, in cache memory, we are going to see the various problematic and performance oriented topics in this particular session. This session will be able to give you a quick overview of what is cache memory and its performance oriented concepts, and followed by the various cache memory oriented problematic topics. Okay. Myself, R. Narendran, working as assistant professor in the Department of Information Technology in Erode Sengundar Engineering College. With no further delay, we shall move on to the session of cache memory in computer architecture. Okay. So we have already seen about what is meant by cache memory in the previous concepts. So, what is cache memory? Let us have a quick overview of what is cache memory. So cache memory is something which is the most fastest memory that a particular system will have, computer will have. So whenever a particular request for a particular resource is going to main memory, the main memory will ask the cache memory which is associated with it whether it is the particular requested file is there in the cache memory. Okay, so in that particular sense, cache memory is so much related to the fastest access of data in terms of memory management hierarchy. Okay, so let us have a look at what are the cache memory basic terms in terms of performance. Okay, so first one is cache hit, second one is cache miss. Okay, if the processor finds the memory location in the cache memory, a cache hit has occurred. Suppose I am going to search and ask or request a processor to find a particular file, whether it is present in the system or not. So whenever we are asking like this, the request will first go to the main memory. Okay, the processor will search whether it is present in the main memory or not. Suppose if it is not present in the main memory, so it will ask the cache memory. So the cache memory will find whether the particular data is present in itself or not. Suppose the um, memory location of that particular requested file is present inside the cache, then it is considered as cache hit. Suppose if the processor does not find the memory location within the cache memory, a cache miss is occurred. Okay, in the case of cache hit, the processor immediately reads or it can able to write the data in the cache file. Okay, so the cache memory basic things involves very important constraints. Okay, next cache performance. So two measures that categorize the performance of the cache are cache hit ratio and the effective access time, EAT. Okay, effective access time. The hit rate or the hit ratio is the total number of times referenced word or in the cache to the total number of memory accesses needed to access that particular cache. Whereas effective access time is the total number of hits into time per hit followed by the sum of total number of misses and time per misses. The total divided by total number of memory accesses needed for catch hit and catch miss. That is called as effective access time. So access time is common, right? So it needs to have a correlation between catch hit numbers and catch miss numbers also. Okay, I again read out a hit ratio is equal to number of times referenced words are in the cache to the total number of memory accesses. Whereas effective access time is the ratio between total number of hits and time per hits, and its sum with total number of misses and time per misses to the total number of memory accesses. Okay, so let us have a look at some of the um, problematic sums. Okay, so a RAM chip has a capacity of 1024, that is 1024 words of 8 bits data, each having 1k into 8 sectors. The number of 2 to 4 decoder with enable line EL, okay, EN, okay, to construct a 16 into 16 RAM from 1 into 8 RAM is. Okay. So what is the thing they have asked? They have given the capacity of 1024 words of each having 8 sectors. The number of 2 by 4 decoders needed to construct a 16 by 16 RAM from 1 by 8 RAM is. So we have to construct a 2 by 4 decoder. So for that, so how much number of 2 by 4 decoders are needed for constructing this particular 16 into 16 RAM? So that is what they have asked. The I will read out the concept. So so a decoder is a combination of circuits. That is a combinational circuit that is having n input lines and maximum of 2 power n output lines. Okay, so that is the decoder. Input line can be one, but the output line is the multiples of so that is a power of 2. So RAM chip size is 1k into 8. Okay, that is 1024 words of 8 bit each. So RAM to construct is 16 to 16. So typical RAM will look like it will be having a chip selection 1 and chip selection 2 pins, and the read and write signal pins, and 7-bit addresses starting from AD0 address data 0 to address data, yeah, that is AD7. So totally 0 to 7 8 bits. So and the output will be 8-bit data bus. Okay, so the secondary one is a 2 by 4 line decoder. In this, the input lines are two, that is A and B are the input, but the output lines are D0, D1, D2, D3. So the highest priority is D4, so that is D3, and the lowest priority input is D0. So it will convert two input lines to four output lines. So that is the decoder. So the solution for the given sum is number of chips required is 16 by 16 to the ratio of 1 is to 8, right? So when we divide, we will get a 16 by 2. So 16 chips vertically with each having two chips horizontally. Okay, so the available decoder is 2 by 4 decoder only. So to construct a 4 by 16 decoder, so hence we are having 4 plus 1 additional of 1, that is 5 decoders are required. So the answer is 5 decoders. So another one, an instruction is decoded when it is kept inside what part? Program counter, instruction register, accumulator, arithmetic logic unit. So which forms part of the instruction. Okay, so an instruction is decoded whenever it is kept inside instruction register, because the instruction register IR is the current register. Okay, so it forms part of CPU's control unit that holds the currently running process. Okay, suppose n number of instructions are taking place in a particular pipeline. So the instruction decoder's work is to find what is the currently running instruction in a particular sequence of instruction. Okay, so the best answer is an instruction is decoded when it is present inside instruction register. Okay, consider the third example. Okay, so in this example, what they are asking. So consider a memory system that takes 25 nanoseconds to service the access of a single 64-bit word. Okay, so the bandwidth of the processor memory interface will be how much uh, number of bytes per second. So the answers given are 320, 160, 640 and 180. So just analyze the question first. So we are having the memory system that is having 25 nanoseconds to service a particular 64-bit word. So what they are asking is, what is the bandwidth of the processor memory? Okay, that is uh, mentioned in terms of megabytes per second. Okay, we'll look into the answer. So 1 byte we will consider as 16 bits. So 64 bits is equal to 8 bytes. So 8 bytes of data can be accessed in 25 seconds. That is what they have given. So in 1 second, the number of bytes accessed is equal to 8 divided by 25 into 10 power 9 bytes. That is 320 megabytes. So the answer will be 320 megabytes. Okay, these are all simple logics only. Okay, so that is for a particular processor to be accessed. That is the bandwidth of the processor memory is 320 megabytes per second in order to access a particular memory system that takes 25 seconds, nanoseconds, to service a 64-bit word. So next question. So assume that L1 catch, the primary catch. Okay, the L1 catch with a hit rate of 70 percentage and L2 catch with a local miss rate of 10 percentage. If there are 1,000 memory accesses initiated by CPU, then the number of access that will find a hit in L2 catches. Okay, I'll put it in this way. So you are given a system, the system is having L1 catch and L2 catch. So primary and secondary catch. The primary catch is having the hit rate of 70%. The secondary catch is having local miss rate of 10 seconds. Hit rate is 70, miss rate is 10 for different catches L1 and L2. So if there are 1,000 memory access that is initiated, in how much number of accesses that will find a hit in L2 catch? Because in L2 miss rate is given, in L1 hit rate is given. They are asking about hit rate of L2 catch. Okay, so the solution will be number of accesses that will find a hit in L2 catch. Okay, is equal to miss rate of L1 into hit rate of L2. Total divided by total number of memory accesses. So 30 percentage of 1,000 instruction plus 90 percentage of 1,000 instruction divided by 1,000 instruction. So it will give you 2,70,000 divided by 1,000. That is finally we will get the answer as 270. So the number of accesses that will find the hit in L2 catch is 270. So okay. Next, what is okay? We'll put it in this way. They are asking the x value in this. So what is x? We will see. The cache has a hit rate of 95 percentage and hit time of 10 nanoseconds. The cache block size is 32 bytes and the word length of the processor is 16 bits. During a catch miss, it takes X nanoseconds to fetch the first word of the block and 5 nanoseconds for fetching each subsequent words. The average memory access time is 15 nanoseconds. Find the value of X. So, average memory access time AMAT is equal to hit time of L1 plus miss rate of L1 into miss penalty of L1. So miss penalty is time to fetch the block from memory. Suppose I am asking to fetch a block of data. What is the time taken to fetch that particular block of data from memory? That is called as miss penalty. So total number of words in block is equal to 32 by 2, which is giving you the answer as 16 words. So as each word is 2 bytes. Okay. So average memory access time is 15 nanoseconds. So 15 is equal to 10 plus 0.05 into miss penalty. So totally, finally, we will get the answer as 25 nanoseconds. So that is the um, average memory access time. Sorry, that is the value of x. Okay, okay. So another question. So consider a directed map cache. So direct mapped cache with 64 blocks and a block size of 16 bytes. Each and every block size is 16 bytes. To what block number does the byte address 1206 map to? Okay, we are having 64 blocks. Each block size is 16 bytes. So in which block the address byte 1206 will be mapped? So our answers are it does not map 6, 11 and 54. Let us see the answer. So block size is equal to 16 bytes. So memory block number is equal to byte address divided by block size. So 1206 divided by 16, we will get 75.3 as an average. The total number, so the given byte address, that is 1206, is part of 75th block. Okay, approximately we can take. So cache block number is equal to memory block number modulus of number of blocks in memory, cache. So 75 modulus of 16, we will get average of 11. So the answer is 11. So, so the block number 11, 1206 address byte is mapped. So students, so in this session we have seen about the various concepts called as cache performance, cache memory basics, followed by different types of um, memory addresses and performance oriented concepts. Okay, so in the upcoming sessions, we can discuss more about some of the arithmetic operations performed and algorithms that are used to make the operations better. Okay, so until that, thank you for listening. We will see in some other lecture video in the upcoming sessions. Thank you for listening. Thank you, one and all.